Okay, let's get started. In this lesson we're going to explore the drag force and its effect on cloth simulation. In vellum, the drag force is divided into two components, normal drag and tangential drag. They provide unequal drag depending on the orientation, and they both are simply multipliers with the global drag force, which is built into the vellum solver properties. Look, the wind drag parameter sets the global drag force in the system, or we can say that it is the amount of air resistance. The wind parameter defines a uniform wind direction. Since this is a drag force, a wind of 0 will act like still air and slow everything down, and a high wind will speed cloth up to that speed. If you uncheck this box, the built-in drag force will be disabled. To ensure that wind drag is a simple drag force, let's dive into the vellum solver assets and see how it was built. Look, this is a basic vellum setup already in dot context, which is hidden, and we usually do not see it, but this is the core of the simulation. So, in this setup, there is a pop wind node, which actually is that built-in drag force. See, the wind drag parameter is tied to the air resistance, the wind parameter tied to the wind velocity, and the checkbox that turns off the drag force is tied to activation. Okay, with drag force, everything is clear. Now let's see what effect it has on simulation. For now let's keep the default drag value and check how it looks. I will zoom out decently to have a lot of room to follow the falling cloth. As you can see, the cloth loses its original shape when it falls, and this is solely due to the drag force because now the atmosphere has a certain density that resists its movement. Now let's reset to 0 the drag force and check again. You saw? The shape has not changed because now the air resistance is 0, which means that cloth moves in a vacuum. That is, no matter how much it falls, the form will remain unchanged. Well, now on the contrary, let's increase the air resistance and look again. See, the initial shape changes almost immediately, and it hardly moves downward because now we have a strong air resistance to movement. Let's keep increasing the air resistance and see what happens. Look, it seems that the cloth is inside the water because the air resists extremely. Now I want to draw your attention to the fact that different parts of the cloth move at different speeds. See, it flows much faster in the tangential direction than in the normal direction, as a result of which the initial form changes. Now I'll show you why this is happening. The drag force multiplier in the normal direction is 100 times greater than in the tangential direction. To make it more visually clear what the tangential direction is, let's create the tangent vectors of this geometry. For that I will use the polyframe node, which can create tangents. Here it is, called tangent U. So, now let's visualize it. Control-click on it, and Houdini will automatically set a visualizer for it. Let's also edit the visualizer and make the lengths of the tangent vectors shorter. Okay, let's take a closer look. Here we go, they perfectly demonstrate the tangential direction. Okay, now let's turn them off and then visualize the normals. As you can see, the direction of the normals is directly perpendicular to the tangents. Well, now I propose to equalize the drag values in both directions and see what happens. Let's increase the tangent drag up to 10 and check the result. Look, what a boring result we got. The air resists equally in all directions, and therefore the initial form barely changes. So, now let's zero out the tangential drag and compare with this. See, it just flows without resistance in a tangential direction. Well, let's also do the opposite, set a small resistance along the normals and a large resistance along the tangents. As you can see, exactly the opposite happening. Okay, now I propose to add directional wind to this, But before that, let's reset both parameters to their defaults and pin some points so that it stay in place and fly like a flag under the wind's influence. That's it. Now we can add wind. Go to the solver settings, then add a wind along the positive x-axis. Since we have set the wind speed quite high, let's decently reduce the wind drag. So, now let's see what we got. Look, the cloth is waving under the wind's influence, and the main reason it is waving is the uneven air resistance between normal and tangential direction. Now let's equalize their values again and see what we get. See, again we have a boring result. The cloth almost does not waving. Well, I also want to create a big contrast between normal and tangential drag and check the result. As you can see, it is now waving even more. Okay, that's all I wanted to show in this example, but I have another example about normal and tangential drag. Let's quickly walk through it and wrap up this topic. So, this time, we'll use this crumpled geometry, and so far all vellum settings by default. Let's play and see. Well, now I suggest cutting it into many pieces, and for that I will use the already familiar edge fracture node. To see the pieces, let's output the primitive pieces attribute, then click this icon so that Houdini automatically sets up the visualizer. Good, now let's increase the number of pieces. That's better, let's go on. So that it does not fall off quickly, I will increase the global drag force. So, before running the simulation and checking the result, let's also equalize the normal and tangential drag values. Okay, let's see what we have now. You see? The pieces don't even fly apart. They go down as if they were one whole piece. Now let's create a contrast between the normal and tangential drag and see what will change. Here we go, their behavior has changed dramatically. Now depending on the angle the resistance force changes, which creates such a beautiful movement. Let's see again. Excellent. I suggest increase the contrast between normal and tangential drag and look again. Now there is almost no movement in the direction of the normals, they only move towards tangents. Well, I also want to change the ratio between normal and tangential drag and see what we get. See, we got the exact opposite. They hardly move in the direction of the tangents, but in the direction of the normals they move without any resistance. Okay, now let's open the geometry spreadsheet and take a look at something. See, the vellum constraint node creates point attributes named drag normal and drag tangent, which the vellum solver knows about, and of course, you can modify these two attributes as you like before they get into the solver. Well, that's all for this lesson. I showed all the most important about the drag. From the next lesson, we will already begin to study everything that is in the geometry section. See you in the next lesson.